Alright, so the Bohr model is kind of an old school understanding of the structure of the atom, where you have your nucleus in the center and then you have your electrons kind of in this circular orbits surrounding the nucleus. And we can say that this is in the first shell, so n equals 1. We're going to get into some of these numbers a little bit deeper in this chapter as well. So this is also referred to as the principal quantum number. But for now, think of it as a shell. So n equals 1, then we have n equals 2, which is our second shell, and n equals 3, which is our third shell. So as an electron moves farther and farther away from the nucleus to a higher numbered shell, it has greater energy. And if you think about it, it's because the nucleus wants to pull those electrons in, right? The nucleus is positive and the electrons are negative. So if it wasn't for the strong nuclear force, right, those electrons want to be closer to the nucleus. So as you move them farther and farther away, it's like lifting something higher and higher off the floor. The higher I lift this ball, the more potential energy is going to be associated with it because gravity wants to pull it in. And so we have that force wanting to pull that electron in. So for this one, n equals 3 has the highest energy. What's so cool about the Bohr model is that it kind of follows what they discovered looking at the photoelectric effect. Even though we're talking about electrons now and not photons, there was this idea that the electrons only exist at discrete quantized energy levels. So that's two big things. Discrete, it's unique. Every single atom, every single element on the periodic table has its own pattern of shells, of orbitals, which creates a distinct pattern of light. And then it's quantized because even though this is a very simplified model, we don't expect to find an electron in between the orbitals. So the electron can exist in the first shell, it can exist in the second shell, but it's not going to exist in shell 1.5. Let's do this part next. So when an electron is hit with a photon, so step 1, we have incoming energy or an incoming photon. If the photon is big enough, right, it's going to dislodge that electron and cause it to go flying. So maybe the electron that's in the second shell, when it gets hit by that photon, it pops up to the third shell. So now we have what's known as an excited electron. And you all know, like, when you get too excited, right? Like, drink a lot of coffee, I don't know, you eat a lot of sugar, eventually you're going to crash. You can't maintain it. It's too unstable because it's high energy at that point. And it's got to come down. So when this comes in, it's absorbing energy. But then when it returns to its initial shell, initial orbital, at that point, it's going to release energy. And when it releases energy, that energy is going to be in the form of light. So these are called transitions. And so we have different electron transitions between the orbitals producing different colors of light. And if you've done flame tests where you take, I don't know, sodium and you put it in flame and you see that it burns that orange-yellow color, that's due to the fact that the fire, the flame, is producing the photons that excite the electrons. And then when they fall back to their original shells, their original orbitals, they release that energy in the form of that orange light. The other term to note here, we have an excited electron, which is in a higher energy shell. And then when it's in its normal state, this is called the ground state. So the ground state is just not excited, it's where it should be. And then the excited state is like the high energy one. To summarize this, so that you can tackle all of your homework problems this week. When you have transitions, and on this page you have a different version of like an energy level diagram. So n equals 1, and there's an energy associated with that, and then there's n equals 2. And then there's joules associated with each level. So we can take the joules from this one and the joules from this one, and we could take the difference. And then if we want the electron to go up, then it would have to absorb that difference. If we want the electron to go back down, then it would have to release in the form of light that difference in energy. And you can do any kind of jumps. Like it doesn't have to be n equals 1 to n equals 2. You can go from n equals 1 all the way up to n equals 3. Or you could go 2 to 6. Every single combination is possible as long as you're not trying to put the electron somewhere in the middle. And if you want to figure out how much energy is needed to do that jump, you subtract the energy levels of the two shells that you're looking at.